In this video, we are starting section 6.1 on the basics of counting. So our goals are to recognize when we multiply versus when we add in counting problems, when and how we use complements in counting problems, and then when and how we apply something called the inclusion-exclusion principle. So in this video, we will talk about counting problems that involve multiplication. So let's get right into an example, which says that 3 Gryffindors and 2 Ravenclaws are auditioning for roles as Quidditch commentators. Okay, so we are in the world of Harry Potter here. If 1 Gryffindor and 1 Ravenclaw must be picked, so 2 total people are picked, how many ways are there to select commentators? Okay, so in this problem, we have to make 2 independent choices. Who we pick for this first spot, who we pick for that second spot. And the problem tells me, well, one of the spots is going to go to a Gryffindor, and there are 3 ways. There are 3. This is the number of ways to pick a Gryffindor. Okay, and there are, because there's 2 Ravenclaws, there are 2. That is the number of ways. Number of ways to pick a Ravenclaw. I'll just abbreviate that, R-A-V. And then what I'm going to do with those, because, you know, the number of choices for the Gryffindor and the number of choices for the Ravenclaw are independent here, I multiply them together, and that gives me 6. And that's the number of ways to choose 1 Gryffindor, I'll call that G, and 1 Ravenclaw, I'll call that R. I could also see this if I listed them out explicitly. So if I listed out the Gryffindors and the Ravenclaws, maybe I'll call the Gryffindors G1, comma G2, comma G3, and the Ravenclaws R1, R2, because there's 2 of them. Then I could form all the combinations just by listing them. So the first Gryffindor could go with the first Ravenclaw, or G1 could go with R2, or G2 could go with R1, or G2 with R2. And then finally G3 could go with R1 and G3 could go with R2. Okay, so there are indeed 6 total pairings of these Gryffindors and Ravenclaws. So the fact that the number of choices for the Gryffindor for the first spot and the number of choices for the Ravenclaw in that second spot, you know, because those numbers were independent, how many choices there were for this first spot didn't affect the number of choices for the second spot. That's what made me multiply those 2 quantities together to get the total. Okay, all right, let's do another problem. Let's up the difficulty this time. So this one says, how many 12-digit passwords can we create if the first and second digits must be different? The third digit must be either 0 or 1, and the last 2 digits must be the same. Okay. So I first want to give you about 2 minutes to try this. So pause the video for 2 minutes to try it. 4, 3, 2, 1, pause it and try it. All right, so hopefully pause it. Let us bring it back together and let's talk about it now. Okay, so for this problem, we are forming a 12-digit password. So the digits are the standard digits, like 0, 1, 2, up until 9. So there's 10 digits, 10 choices for each of these spots in the password. And my password has to have 12 digits. So there's spot number 1 and spot number 2 and 3 and 4, 5, 6, 7, 8, 9, 10, 11, 12. So I'm just going to put little slots like this for each of the spots where we are going to be placing a digit or picking a digit. So let's see. So for this problem, we are going to be making 12 independent choices. And I'll talk more in a little while about why these actually are independent. And what does that mean more precisely? So the first and second digits must be different. So, you know, how could I deal with that? Well, for this first digit, there are 10 things I could pick. There are 10 choices, because it could be any one of these integers between 0 and 9. 10 choices for the first digit. Okay, and then, well, whatever I pick there, for example, if I were to pick the number 3, well, the second digit has to be different. It could be anything except 3. So once I pick that first digit, there are now just 9 remaining. 9 remaining choices for the second digit, because it has to be different from the first. It's got to be different from the first. And no matter what I pick for the first, like even if I were to pick a 5, there's still 9 remaining choices for that second digit. Okay, cool. What about for the third digit? Well, the third digit's got to be either 0 or 1. So there are only 2 choices for this third digit. It could be 0 or it could be 1. Okay. And then let's jump ahead to the last 2 digits. The last 2 digits have to be the same. So if I focus on those last 2, if I think about this second to last one first, maybe, well, there's no restrictions on that. So there's 10 choices for this. It could be any one of the digits between 0 and 9. But once I pick that digit, like for example, if this was the digit 2, well, the last digit is fixed. It's got to match that. It's got to be a 2 also. So once I pick this second to last digit, there's only 1 choice for the very last one. It has to be the same as the previous digit. Same as the previous digit. So once the second to last one is picked, well, that leaves me with just 1 choice for that last one, because it's got to be the same. Okay, and then, well, what about all of these other digits in between? There's no limitations on what they are, so they could be any one of the 10 digits. So there are 10 choices for each of these digits in the middle. So, my final answer is I take each of these numbers and multiply them together. So I'll get 10 times 9 times 2. And then there's a bunch of 10s that we have. If I count them all up there in the middle, there's actually 8 of them. So times 10 to the 8. And then finally, I get a times 1 at the end. Okay, so 10 times 10 to the 8 becomes 10 to the 9. And then 9 times 2 times 1 is 18. And it doesn't really say I have to simplify my final answer. So I could work this out if I wanted to, because multiplying by 10 to the 9 isn't all that bad. Like this will end up being 18 billion. But let me just leave it like this. So there are this many passwords that satisfy these conditions. Okay. So I want to end this video by summarizing, the results that we saw in these examples about when do we multiply. So when we are selecting multiple objects independently, and I mean independently in the following sense, the number of ways in which we choose the first object doesn't affect the number of ways to choose the second object, and so on. Then we multiply the number of choices for each spot. So in the context of the previous example, it was certainly true that once I picked this first digit, like for example, if it was a 3, then the second digit, did depend on the first one. Like it couldn't be a 3. But I'm using this word independently to refer to the fact that, well, the number of choices for this first digit, that did not impact the number of choices for the second digit. Like once I picked the number of choices for the first digit was 10, and regardless of what that digit was, there were always going to be 9 choices for the second digit. That's the sense I mean this word independent here. Okay, so in general, if I'm selecting k objects, and there are A1 ways to pick the first object, A2 ways to pick the second object, and so on until AK ways to pick the kth object, well then, the total number of ways to pick these k objects are going to be these things multiplied. So A1 times A2 times A3 ... times AK. All of them are going to get multiplied together. Okay, so when we have independent choices like this for each spot in counting problems, we end up multiplying together. So in the next video, we will talk about, well, when do we add things together in counting problems?